Hello everyone. Thanks to everyone for watching this video. My name is Qida. I am an architect and engineer. Today's video is titled Plane Stress, and it is going to provide you the fundamentals of plane stress and also the plane elements. I am going to give you an overview of what I am covering in today's video. First at all, it is a bit of background to the topic, and then focus on the constitutive model and the plane elements before wrapping up with conclusions. Analyzing solid mechanics problems in 3 dimensions can be really hard work, and it can get very complicated very fast. Fortunately, in a lot of cases, there are some simplifications we can use to reduce a 3-dimensional problem to a 2-dimensional one, making it much easier to solve. The 2 main simplifications which are frequently used in soil mechanics and the plane stress and plane strain conditions. In this video, we are going to take a look at plane stress. So what does plane stress mean? A component is said to be in a condition of plane stress when all the stress is acting on it are in the same plane. A surprising number of common engineering problems can be approximated to plane stress conditions. It is most relevant for the analysis of thin components. Let's take a look at an example. To determine whether we could model this perforated plate using plane stress assumptions, we need to see whether it is reasonable to assume that all stresses are acting in the same plane. All the loads are applied in the same plane, the XY plane, so that's a good start. But having all loads acting in the same plane is not enough for the plane stress condition to be met, as we could still have stresses in the Z direction. This is where the thickness of the plate comes into it. We know that normal and shear stresses at the free surface are always 0. This means that the stresses on the top and bottom faces of the plate must be 0. And because this plate is very thin, there can't be much variation in stress through the plate's thickness, meaning that the stresses in the Z direction will be close to 0 all the way through the plate, because the only non-zero stresses are acting in the XY plane. A condition of plane stress applies. Of course, in reality, the stresses in the Z direction are unlikely to be exactly 0. Deciding whether a plane stress condition is applicable will always require a degree of engineering judgment. Why is the plane stress assumption useful? We can answer by taking a look at a stress element in our perforated plate. The stresses at a single point are defined by 6 different stress components, 3 normal stresses and 3 shear stresses. For plane stress conditions, sigma z, tau xz, and tau yz are equal to 0. This means that the 6 components defining the stress at a point are reduced to just the 3 components, sigma x, sigma y, and tau xy. This is a 2-dimensional problem which will be much easier to solve. In this video, we consider only isotropic, homogeneous materials, and the 4-node quadrilateral. The problem is defined in a domain A bounded by big gamma. The plane stress problem considers 2 global displacements, u and v, defined in global directions x and y respectively. Strengths are obtained by derivation of displacement. By assuming a linear elastic material, we obtain stress matrix, where E is the modulus of elasticity and mu is the Poisson's coefficient. The static equilibrium equations are defined, where Bx and By are body forces. According to the potential energy system, the displacement functions can be tried to obtain the minimum potential energy. The potential energy equation can be defined, where U is the elastic strain deformation and W is the energy produced by the external forces. Now we know the constitutive model and move to finite element discretization. Given a domain denoted by A and a boundary denoted by big gamma, an n-noded finite element displacement vector by 2 times n degrees of freedom. The displacement vector in each element is interpolated by the nodal displacement, where Ni denotes the element shape functions. Through the mathematical derivation, we can introduce these expressions into the total potential energy and obtain the element stiffness matrix. The strain vector can be obtained by derivation of the displacement. This matrix is needed for computation of the stiffness matrix and the stress vector at each element. In matrix form, we can write relations using the Jacobian operator, relating natural and global coordinates. The derivatives with respect to the global coordinates can be found. The stiffness matrix is obtained. Note that B depends on the element natural coordinates, C, eta. dTj is the determinant of the Jacobian matrix, and h is the thickness of the plate. The integral in the stiffness matrix is computed numerically by Gauss quadrature in 2 dimensions. In the 4-node element, we can use a 2 times 2 numerical integration for exact integration. The Gauss quadrature in 2 dimensions replaces the integration by a summation over Gauss points, where P and Q are the number of integrating points in the C, eta directions, respectively, and Wi, Wj are the corresponding weights for some integration orders. In this case, the stiffness matrix can be computed using 2 times 2 Gauss points. Now I want to provide an introduction to using Gauss quadrature to do numerical integration. It's a method which is based on discretizing the integral. So the idea is we replace an integral from say -1 to 1 of f of c dc with an approximation which is given by the sum of k terms. So we are summing from k equal to 1 to n of some weight evaluated at 8k times f of ci. We just have a weighted sum of the function values with weights given the particular c values. For a simple model, we are going to start by using an approximation to f, which is a linear one. The weight a1 times 1 is equal to the integral from -1 to 1 of 1 dc, which is equal to 2. Then what we do is we consider the terms which are to do with c. We have a1 times our new f, which is going to c1, is equal to the integral from -1 to 1 of c dc. Solving the 2 equations, we can obtain weight a1 equal to 2 and c1 equal to 0. If we consider a cubic model, there are 2 Gauss points. Then we can solve the 4 equations and obtain a1 and a2 equal to 1, c1 equal to -1 over root of 3, c2 equal to +1 over root of 3. According to the same procedure, we can obtain the weights and Gauss points of force power shown in the table. Now we can use the Gauss quadrature to compute the stiffness matrix. For a system of planes, the contribution of each element must be assembled. For example, we consider 6 nodes and 2 elements. Summing the contribution of all elements, we obtain the strain energy and the energy done by the external forces. The stiffness matrix and the vector of equivalent forces are then assembled. We then obtain a global system of equations to be solved after the imposition of the boundary conditions. Now we consider a thin plate under uniform shear forces. In this case, both U and V are fixed at x equal to 0. The applied force is in the -y direction, so care must be taken to ensure that degrees of freedom are properly assigned. We show the finite mesh size, 1 times 1, half times half, quarter times quarter, 0.1 times 0.1, 0.05 times 0.05, respectively. From the sensitivity analysis of finite elements, it is easy to know when the mesh size reaches the 0.1 times 0.1. The answer is convergence. From conclusions, what we learned? A suitable number of mesh size are finite elements can be useful to help the answer convergence. All boundary conditions are equivalent to the nodes of plane elements. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching